Thanks for coming. So today I wish to talk about an aspect of science which is both rudimentary and profound: measurement. In Johnny fashion, I want to frame this discussion around the works of some of the great masters in the foundation of measurement: Maxwell, Peirce, and Planck. Their efforts, which span one of the most consequential periods in the development of physics, continue to this day in matters as diverse as quantum foundations, high precision metrology, and the search for extraterrestrial intelligence, or SETI. Is the volume good? Okay. Now, what was it that they were trying to do? I will argue that each attempted to make our measurements absolute. What that means exactly will vary a bit in each case. Why care about making measurements absolute? To know absolute reality. If we have come to know absolute reality, it is in a piecemeal and minor way, but each of these scientists have made a noble contribution to the quest, and I'll give some evidence of that. The history of measurement I'm giving here is a partial but relatively standard one. What I hope to add is an explanation of the connection between absolute measurement to the question of absolute reality, a connection often left obscure. So we'll start with Maxwell, who I think is familiar to most of us in the room. I'll just make explicit that Maxwell is, of course, one of the great founders, probably the greatest founder of theoretical electricity and magnetism, the theory of electricity and magnetism, which is quite famous in particular for leading to Einstein's special relativity. And that theory will get mentioned in passing as we go through, although that's not the focus of today. I want to start by considering a passage encountered by Johnnies in their junior laboratory class, which tends to cause confusion and debate. This is from the preface to the first edition of Maxwell's treatise on electricity and magnetism. Quote, "Having thus obtained the data for a mathematical theory of electromagnetism, and having shown how this theory may be applied to the calculation of phenomena, I shall endeavor to place in as clear a light as I can the relations between the mathematical form of this theory and that of the fundamental science of dynamics, in order that we may be in some degree prepared to determine the kind of dynamical phenomena among which we are to look for illustrations or explanations of electromagnetic phenomena." Largely, our discussion on this point centers on the meaning of dynamical. If someone recalls the classical distinction between statics, the physics of forces in equilibrium, kinematics, the physics of motion, and dynamics, the physics of forces as causes of motion, the statement starts to make more sense. Maxwell's aim would then be to bring electricity and magnetism into the fold of ordinary dynamical physics, where statics and kinematics are seen merely as special cases of dynamics. As Newton showed optics to be a species of dynamics with his corpuscular theory of light. This unificationist impulse can further be seen in the work of one of Maxwell's heroes, the great experimentalist Michael Faraday. Alternatively, to understand Maxwell's understanding of dynamics, one can do the very un-Johnny thing and take a look at a secondary text by a supposed expert. Now, I happen to just have on hand a book on Maxwell by John Hendry. And here, it's the first chapter after the introduction and the table of contents there. Here we find an interesting contextualization of Maxwell's remarks in an opposition between mechanistic and dynamistic conceptions of physics in the 19th century. What are these two ways of approaching physics? We might first get a sense of the distinction by lining up some of the names associated with each camp. On the mechanist side, we have Descartes, Newton, Locke, Condillac, Laplace. On the dynamicist side, we have Leibniz, Kant, Faraday, Boscovich, Whewell, and Lagrange. While no simple statement of those two conceptions can do justice to the variety of contributions and philosophies associated with the set of names, these two sets of names, we can use a working distinction between the two in terms of what they count as a good physical explanation. A good mechanistic explanation explains some phenomenon in terms of force interactions of distinct particles of matter. The mechanist privileges separability, visualizability, and constructibility in their explanations. The standards for a dynamicist explanation are a bit more vague. A good dynamicist explanation explains some phenomenon in terms of a general underlying principle, like the conservation of energy, without recourse to any specific mechanistic model. A natural dynamicist philosophy is energeticism, which holds that all physical phenomena are constituted by and explainable by reference to changes in states of energy, but there are other examples of dynamicist explanatory schemes. I say that dynamicist explanation requires no specific mechanistic model because some will be familiar with the multitude of mechanistic models Maxwell uses to illustrate and motivate his development of electromagnetism, like the well-known vortex and idle wheel model of the electromagnetic field developed in his 1861 paper on physical lines of force. I think usually in the source text we skip the parts that go into details of this. Vague way to understand what's going on with the model is that the rotational strain in the electric medium produced by these vortices, so these rotations, are supposed to explain phenomena like the Faraday effect, which is the rotation of the polarization of light passing through a magnetized medium. Now, I agree with Hendry that such mechanistic models are best understood as analogies to spur on mathematical development rather than hypotheses which purport to be true explanations of the phenomena for Maxwell. Going back to the treatise, we find some support for this reading in the quote I've already given. There, the purpose of connecting the mathematical theory of electromagnetism to the fundamental science of dynamics is to prepare the way for dynamical illustrations or explanations of electromagnetic phenomena. There are ambiguities in the strength of this claim. Hendry, who's in favor of a dynamicist reading of Maxwell, would emphasize the role of dynamical illustrations, while a mechanist might emphasize the role of dynamical explanations in contrast. We might even accept that these mechanical models are indeed explanations with the mechanist, but preserve the dynamicist reading of Maxwell by further distinguishing what we can call how actually explanations from how possibly explanations. And I won't go into that, but maybe we can talk about that in the Q&A. Regardless, these ambiguities show some limitation with the contextualist approach. So let's explore a different approach to interpreting Maxwell. Let's go back to the text. At the beginning of the paragraph that I quoted from earlier, goes like this. In the following treatise, I propose to describe the most important of these phenomena to show how they may be subjected to measurement and to trace the mathematical connections of the quantities measured. End quote. This is an accurate description of the method of theory building that is exhibited in the treatise. First, the measurable quantities of various electromagnetic phenomena are defined, and only then is a theoretical superstructure built on the foundations of those quantities. Maxwell goes on to say, later in the preface, quote, "The most important aspect of any phenomenon from a mathematical point of view is that of a measurable quantity. I shall therefore consider electrical phenomena chiefly with a view to their measurement, describing the methods of measurement and defining the standards on which they depend." End quote. I suggest that we interpret Maxwell's unificationist project, uniting electromagnetism with dynamics, by focusing on his foundational theory of measurement. In his preliminary on the measurement of quantities, Maxwell gives influential expositions of the foundations of what are now known as dimensional analysis and vector analysis, and my focus will be on the former, dimensional analysis, today. It is in the exposition of dimensional analysis that Maxwell affects the unification of electromagnetism and dynamics that prepares the way for dynamical models of electromagnetic phenomena, however you interpret the significance of those models, whether they're illustrations or actual robust explanations. The pivotal paragraph in the preliminary reads so: "There must be as many different units as there are different kinds of quantities to be measured, but in all dynamical sciences it is possible to define these units in terms of the three fundamental units of length, time, and mass. Thus the units of area in a volume are defined respectively as the square and the cube, whose lengths are the unit Thus, the units of area and of volume are defined respectively as the square and the cube, whose sides are the unit of length. End quote. The relation of derivative units to fundamental units gives the dimension of the derivative dynamical quantities, which now include electromagnetic quantities, so that as area has a second dimension in length and volume has a third dimension in length, the electrostatic unit of charge has 3/2 dimension in length, minus 1 dimension in time, and half dimension in mass. And here you can see that dimension and others. The dimensions of the electrostatic unit of charge are determined by the Coulomb equation and the condition of dimensional homogeneity, which states that the dimensions of every term of an equation must be the same. Forces must equal forces, and lengths must equal lengths, and so on. Now there's a question, why adopt such a condition as dimensional homogeneity? For Maxwell, the aim is international communicability. So he says, the formulae at which we arrive must be such that a person of any nation, by substituting for the different symbols the numerical value of the quantities as defined by his own national units, would arrive at a true result. End quote. This means defining an absolute unit system, which is invariant under an arbitrary choice of national unit standards. This is provided by a dynamical system of dimensions. In other words, Maxwell's equations must be valid whether one is working with the metric system or the imperial system. I will just mention as an aside that Maxwell in fact defines and relates two distinct absolute unit systems, the electrostatic and the electromagnetic, as you see with these two columns. There may be lurking problems with that, but I'll set that aside. Maxwell had good reason to be concerned with the international communicability of scientific laws. Over the course of the 19th century, science became more and more internationalized, especially geodesy, which I'll say more about shortly. Further, electrical units needed to be standardized between engineers and physicists for projects like the transatlantic telegraph cable. Maxwell joined a committee on electrical standards formed by the British Association for the Advancement of Science in 1861, which was led by his friend William Thomson, who you likely know as Lord Kelvin, who's quite famous for his work on thermodynamics. It is in work for this committee, in collaboration with Fleming Jenkin, an engineer, that Maxwell developed his dimensional formulae and his conception of absolute units. It is worth adding in a bit more context at this juncture. In the wake of various exhibitions and congresses concerned with displaying and promoting the international progress of science and its industrial results, the United Kingdom made use of the metric system legal in 1864, though an earlier 1861 bill for the full adoption of the metric system failed in the House of Lords. It was not until 1973 that the UK adopted the metric system fully. Surely the need for electrical standards developed by Maxwell and others to be acceptable to other nations who used the metric system at that time, in part motivated the allowance of the metric system in British science. Spurred on by the revolutionary dreams of rationalization, the metric system has its origins in France and in the French Revolution. The meter was to be based on a stable universal natural phenomenon. Naturally, it was defined to be 1/10,000,000th of the Peirce equatorial meridian, which is to say 1/10,000,000th of the line from the North Pole to the equator that passes through Paris. Maxwell, taking the long view, remarked on the instability of the Earth's figure in his 1870 presidential address to the Math and Science section of the BAS, claiming that its figure, the Earth's figure, is less permanent than the properties of fundamental molecules, since the Earth is susceptible to cooling and so contraction, meteorites, and variations in rotational speed, which would all sort of change the foundational definition of the meter. And you can probably add other variations in the size of the Earth as well, size and shape. In the treatise, Maxwell also remarks on the desirability of a more absolute length standard, preempting the sort of standard that gets adopted in the 20th century. Quote, in the present state of science, the most universal standard of length which we could assume would be the wavelength in vacuum of a particular kind of light, emitted by some widely diffused substance, such as sodium, which has well-defined lines in its spectrum. Such a standard would be independent of any changes in the dimensions of the Earth and should be adopted by those who expect their writings to be more permanent than that body. End quote. While, as far as I know, Maxwell does not further elaborate on the desirability of absolute standards, he provides good reasons and lasting models of absolute unit systems, which allow for changes in standards, hopefully trending towards the more absolute. Maxwell's work founds the quest for absolute measurement on two powerful motivations: international communication and the unification of physics. But a connection between absolute measurement and absolute reality is largely left implicit. Maxwell often leaves such considerations for the metaphysician. For a more robust connection between our scientific methodology and the metaphysics of the world, we must turn to the peculiar realism of Charles Sanders Peirce. So Peirce might be a little less familiar to some of us here. He's most often known as the founder or the father of the philosophy called American pragmatism. He was good friends with William James, and he also taught John Dewey and was influential on his thinking. And largely the way he considered his focus was on logic. So he did a lot of work on probability, on induction, but his career, as you can see here, involved a lot of different scientific endeavors, which we'll hear about today. So it's probably best to start with a consideration of Peirce's day job, which in fact led to his crossing paths with Maxwell, at least once. In 1872, the superintendent of the U.S. Coast Survey, Benjamin Peirce, a Harvard mathematician and astronomer, assigned his son Charles to the position of acting head of the D.C. office. During an 1875 trip to Europe, motivated by the need to get American geodesy up to European standards, Peirce met with Maxwell, apparently to discuss pendulum theory. I don't know if I haven't done any archival work or anything for this, so I don't know if they discussed a light length standard. If they did, it would probably be reported in some of the literature. But I'll talk more about that standard anyway later. Further, Peirce was going to Europe to retrieve a precision pendulum from a German firm designed by the famed astronomer Bessel. You might have heard of his surveys, his astronomical surveys. Peirce's trip to Europe, which would not be his last, highlights the internationalization of science in this period, which I've already mentioned. It is already particularly significant that Peirce's object on this trip was one of his objects at least, was the precision pendulum. Why the interest in pendulums? In 1878, the U.S. Coast Survey was renamed the United States Coast and Geodetic Survey, which indicates the rising significance of geodesy, which is the science of measuring the Earth, for the governmental body. Geodetic work had many political and technological purposes, from mapping the vast U.S. interior for homesteading, to managing borders and the new purchase of Alaska, to the laying down of telegraph wire and railroads across the nation. Further, confirmation of the degree of the Earth's polar flattening due to its rotation was scientifically important as a test of Newton's gravitational model, especially as elaborated upon by Laplace. However, the figure of the Earth cannot be determined solely in one's backyard and requires data from around the globe, making geodesy an essentially international science. A subdiscipline of geodesy, gravimetrics, relied heavily on high-precision pendulums. Given that the strength of gravity varies with the distance from the center of the Earth, variations in gravity can measure the figure of the Earth. The variation in a pendulum's swing period is a proxy for the strength of gravity, hence the need for high precision and Peirce's interest in metrology, which would be a lifelong interest. Metrology being the science of measurement, which he considered as logic in action. Peirce made many contributions to the theory of pendulum gravimetrics, for example, determining a systematic error due to the flexure of pendulum stands, and even designed invariable reversible pendulums, which eliminated this source of error. And so this on the left here is one such pendulum designed by Peirce and used by Peirce. I don't know enough about pendulum theory to explain exactly how it fixes the errors. But one aspect of it is that the cylindrical sort of case of the pendulum, the symmetry of that eliminates some errors. And these are like double pendulums that kind of cancel out each other, cancel out sort of lateral motion. I should also say that this image I stole from Robert Crease, who's his article on Peirce and the first absolute measurement standard, and he also has this in a book of his. He's a philosopher at Stony Brook. And if you want to hear more about sort of the bloody details of Peirce's work in geodesy, I recommend this paper by Victor Lenzen, who, if I remember right, I think who was a physicist, but ended up being the first person to organize Peirce's papers after he died. Peirce's internationally oriented scientific work in geodesy provides important context for his famous Popular Science Monthly articles of 1877 and 1878, in which he provides a logic for chance and scientific methodology, as well as early statements of the philosophy which came to be known as American pragmatism. I wish here to focus on the first two essays of this series, I believe of 5, the fixation of belief and how to make our ideas clear. In the first, Peirce compares several methods of fixing our beliefs in the face of the inquiry-inducing irritation of doubt. These are, first, the method of tenacity, wherein we cling to our current beliefs; the method of authority, wherein we have our beliefs determined for us; the a priori method, wherein our beliefs are determined by our natural reason; and finally, the method of science. While Peirce thinks all of these methods have something to commend them, he really does. Peirce holds that all of them, besides the method of science, are ultimately unstable in the face of our social impulse. This social impulse being that the fact that either our contemporaries or past peoples have or have had differing views from ours inevitably causes doubt, which is an unfixing of belief. Now, what is this method of science? Peirce articulates two important aspects of this method. Quote, "To satisfy our doubts, therefore, it is necessary that a method should be found by which our beliefs may be caused by nothing human, but by some external permanency, by something upon which our thinking has no effect." End quote. As we'll see in a bit, we might call this condition the reality condition of the scientific method. Secondly, Peirce says, our external permanency would not be external in our sense if it was restricted in its influence to one individual. It must be something which affects or might affect every man. End quote. We might characterize this as the long-run intersubjective agreement condition on the method of science. Peirce puts this fundamental hypothesis of the method of science more directly by saying it is, 1, a commitment to real things, and 2, their eventual knowability. Discussions of the second essay, How to Make Our Ideas Clear, rightfully focus on Peirce's articulation of the pragmatic maxim. And there are various ways of characterizing it, but you might characterize it as that the meaning or the truth of a claim is constituted by its empirical manifestations, whether these empirical manifestations are experimental confirmations, or maybe even the results of believing in the claim. While there's much of interest and controversy surrounding various interpretations of this maxim, I instead want to focus on the further articulation of realism, which picks up where the fixation of belief leaves off. Late in How to Make Our Ideas Clear, Peirce makes a further connection between what I have distinguished as the reality condition and the intersubjective condition of the method of science. Quote, the opinion which is fated to be ultimately agreed to by all who investigate is what we mean by truth, and the object represented in this opinion is the real. That is the way I would explain reality. End quote. So it appears that the intersubjective condition provides an explanation for the reality condition, that in the long run all scientific agents come to a unified agreement is supposed to be an account of what the mind independence of reality consists in. To this we might add that in this hypothetical long run, it is the case that our beliefs are fixed and that doubt can no longer work its way in. Peirce also provides an example of such an emerging consensus, which connects back to his metrological work. Quote, "One man may investigate the velocity of light by studying the transits of Venus and the aberrations of stars. Another by the oppositions of Mars and the eclipses of Jupiter's satellites. A third by the method of Fizeau. A fourth by that of Foucault. A fifth by the motions and curves of Lissajous. A sixth, seventh, and eighth, and ninth may follow the different methods of comparing the measures of statical and dynamical electricity. They may at first obtain different results, but as each perfects his method and his processes, the results will move steadily towards a destined center. So with all scientific research." End quote. The consilience and convergence of multiple methods of determining the speed of light explain its objective reality. High precision physics, therefore, is evidence for an absolute reality. Peirce's account provides a link between absolute measurement and absolute reality. Absolute measures, particularly absolute standards, provide a point of agreement for all scientific agents to fix their beliefs to. By doing so, these absolute standards, if ever finally found, would constitute bits of absolute reality itself. Community provides the bridge between absolute measurement and absolute reality. This brings me back to the other aspect of Peirce's metrological investigations that were alluded to earlier. Peirce, in consonance with Maxwell's suggestions, worked towards the first spectrographic meter standard, which he called a spectrometer, which is not to be confused with a spectrometer. Peirce's interest and competence in spectroscopy dates back at least to his assistantship at the Harvard Observatory, another position arranged for by his father, if not his chemistry degree at Harvard. Similar to Maxwell's complaints regarding the variability of the Earth's figure, Peirce complained that the metallic bar meter standard was subject to too much variation for the degree of precision needed in the sciences, particularly geodesy. Spectra, the characteristic color profile of a material, whether they be solar or atomic, are produced by the passing of the light from the material through a diffraction prism or a grating. Think of Newton's demonstration of the color spectra of solar light, the Pink Floyd style prism. High precision spectra, like that of elements, requires high precision gratings. Peirce sourced his gratings from Louis Rutherford, an amateur astronomer who was at the cutting edge of precision instrument making. These gratings, on the left is an example of one of these. These gratings were produced by the passing of a diamond stylus over a piece of glass or metal advanced by a micrometer screw. Such diffraction gratings could get around 13,000 lines per inch at that time. Peirce had a very difficult and tumultuous life and did not get to pursue this metrological work to completion. However, diffraction gratings became ever more precise, and Peirce's publications on the prospects of the spectrometer did inspire Michelson and Morley to get the job done. Systematic errors in Peirce's attempts with elemental sodium were fixed by the Michelson-Morley interferometer instrument design, famous for its use in failed attempts to measure ether drift, leading to Einstein's theory of special relativity. Though it wasn't until 1960 that the meter was officially redefined on this optical basis. Although, from what I saw, I think some particular sub-communities adopted it earlier. I think astronomers adopted it pretty early. So on to Planck. Max Planck is one of the initiators of the quantum revolution of the 20th century. This was after the shock of relativity theory and before the shock of the Nazi Party's electoral victory in Germany. Both in science and in politics, the world Planck grew up in, matured in, was destroyed. His life was filled with tragedy, having outlived his first wife and 4 of his 5 children, one of whom his great influence, even during the time of Nazi power, failed to spare his own son from execution by the Nazis. This son, Aaron Planck, was involved in a failed plot to assassinate Adolf Hitler. It is remarkable in all this upheaval and destruction that Planck held fast to his faith in God and his faith in absolute reality. Let's begin by noting the rigor to which Planck held the standard of absoluteness. As early as the turn of the 20th century, Planck introduced the notion of natural units as a more absolute alternative to even the so-called absolute standards desired by Maxwell and Peirce, and then effectuated by people like Michelson and Morley. I have a long Planck quote here. All the systems of units which have hitherto been employed, including the so-called absolute CGS or metric system, owe their origin to the coincidence of accidental circumstances, inasmuch as the choice of the units lying at the base of every system has been made, not according to the general points of view which would necessarily retain their importance for all places and all times, but essentially with reference to the special needs of our terrestrial civilization. Thus, the units of length and time were derived from the present dimensions and motion of our planet, and the units of mass and temperature from the density and the most important temperature points of water, as being the liquid which plays the most important part on the surface of the Earth. It would be no less arbitrary if, let us say, the invariable wavelength of sodium light were taken as the unit of length. For, again, the particular choice of sodium from among the many chemical elements could be justified only, perhaps, by its common occurrence on the Earth, or by its double line, which is in the range of our vision, but is by no means the only one of its kind. Hence, it is quite conceivable that at some other time, under changed external conditions, every one of the systems of units which have so far been adopted for use might lose, in part or wholly, its original natural significance. End quote. Planck goes on to suggest a less parochial alternative based on the constants. One that would go on to be named for himself, the quantum of action, and one that would be named after Boltzmann, which relates temperature and energy, in combination with the gravitational constant and the speed of light, which was elevated to a constant with the onset of the theory of special relativity. The natural units defined in terms of these constants are to be independent of special bodies or substances and necessarily retain their significance for all times and all environments, terrestrial and human or otherwise. What was an international invariance standard of absolute units is now an intergalactic standard. Planck's natural units are to hold what he calls a natural significance, as long as and wherever the laws of physics are valid. One might wonder whether Planck would have been disappointed with the contents of the record sent on the Voyager probes in 1977 into interstellar space. The content of the record, the Voyager record, is highly anthropocentric, with the cover having directions to the Earth and the record itself having images and sounds from the Earth. These are unlikely to have a natural significance. On the other hand, after an initial calibration circle and a lesson in arithmetic, the record defines units in a way more agreeable to Planck's conception of natural units. Rather than define units in terms of constants which figure in the fundamental laws, the authors of the Voyager record, were a committee headed by Carl Sagan, used the hydrogen atom as its foundational source for its units. The transition of an electron spin state, depicted on the top left of the image, and its radiation on the top right, the corresponding radiation to the switch of states, is used to define natural units of mass, length, and time, which are then related to ordinary terrestrial units like the centimeter, the gram, and the second. And you can see some of the conversions there. A series of further scientific diagrams depicting astronomical, chemical, and biological facts are built on the measurement system established in this image. The existence of this alternative system of natural units does raise an issue for Planck's notion of natural significance, which I'll simply leave as an open question. There are in fact a number of possible unit systems, of natural unit systems, and a number that are or have been in use. And it sort of depends where you are in the physics community. If you're in if you're in particle physics, you'll maybe use Planck units, but if you're doing something else, you might use some other natural unit system. In fact, George Stoney of the Stony units on that column, suggested a system of natural units about 25 years before Planck. Contemporarily, we define natural unit systems by setting a subset of the fundamental constants to unity and doing some natural dimensional reductions and then determining the scale of whatever unit quantities like mass are of interest. I think there's an ongoing confusion about the seeming arbitrariness and conventionality of a choice of natural units and the seeming significance of some such defined units. It's often said that our search for quantum gravity should focus on the Planck scale, which are sort of, you can characterize it either by the length defined by the Planck units or the energy scale that corresponds to the Planck mass. There's some work on that happening now, I think, to clarify the issue, but I think it's still a bit of a confusion. But I'll set that aside. The constants of nature continue to have a major role in Planck's philosophy of science up until the end of his life. In a 1947 essay titled Religion and Natural Science, Planck makes the claim that the constants are immutable building blocks of the edifice of theoretical physics. But then he raises a question as to their nature. Quote, "What is the real meaning of these constants? Are they, in the last analysis, inventions of the inquiring mind of man, or do they possess a real meaning independent of human intelligence?" End quote. The first view, that they're inventions of the mind, Planck attributes to his longtime philosophical enemies, the positivists. Indeed, he claims that the acceptance of the existence of such constants is proof against the positivist position, as their existence is, quote, palpable proof of the existence in nature of something real and independent of every human measurement, end quote. And as the existence of absolute constants is necessary to scientific practice, according to Planck, the positivist position is untenable. Planck, in fact, elevates the constants to the ultimate goals of scientific research, the ultimate elements of reality that orient our practice. In another 1947 essay titled Phantom Problems in Science, he says, "In the realm of exact science, there are the values of absolute constants, such as the elementary quantum of electricity or the elementary quantum of action, and many others. These constants always prove to be the same, regardless of the method used for measuring them. The endeavor to discover them and to trace all physical and chemical processes back to them is the very thing that may be called the ultimate goal of scientific research and study." End quote. With Planck, we see a complete alignment of the quest for absolute measurement and the quest for absolute reality. Now, you might be thinking, what about quantum mechanics? Doesn't it show that there's a limit in our approach to absolute measurements? This limitation not being merely that of a Peircean limit or a Kantian regulatory principle, but a real concrete limit in the present. Doesn't Planck's absolute realism get undermined by his own intellectual offspring? Now, I can't tell a full story of here for several reasons, both historical in terms of, and also in terms of my own competence, as to how quantum mechanics is to be dealt with by Planck or by anyone else. But I'll say just a little bit about how Planck proposes to solve the issue, because he didn't ignore the problem. So first, I should say that Planck presents the problem raised by quantum mechanics as one regarding causality, which is already itself maybe controversial depending on your point of view. In particular, he characterizes quantum mechanics as challenging the notion of the principle of causation that holds that every physical event is in principle exactly predictable on the basis of some earlier established facts. This is determinism. Planck recognizes quantum principles like Heisenberg's uncertainty principle do indeed limit our predictive capacities, but he thinks, or at least seems to think, that this need not undermine the principle of causality in full generality. In multiple essays, Planck posits the existence of an ideal observer, a supreme wisdom or Laplacian demon, with perfect knowledge of the complete state of the universe. For this being, quantum mechanics is assumed to be of no consequence. Now, whether this kind of response is tenable in light of various no-go theorems and restrictions on hidden variable theories, like coming from violations of Bell inequalities or various other no-go theorems, I'm unsure, so I'll remain silent on Ultimately, Planck ties his quest for absolute reality to the quest for God, both providing a stable foundation for a tumultuous life. In his 1947 essay, again, Religion and Natural Science, he ends it by saying, "Religion and natural science are fighting a joint battle in an incessant, never-relaxing crusade against skepticism and against dogmatism, against disbelief and against superstition, and the rallying cry in this crusade has always been and always will be, unto God."